Iain was given the task of, very hard task, of taking that stuff for the Gaussian mean problem and seeing what he could say in Poisson problems. And he brought that expertise, that deep mathematical statistical expertise that he has developed much and flourished in to Stanford, and we're really grateful to be able to hear from him today.
Thank you. So thank you for that very generous introduction. We were chatting yesterday, and this is interesting, about the Larry Brown's paper on the central limit theorem via Fisher information. And Andrew was telling me that he would walk on his way to the ISL, the Information Systems Lab, through the statistics department, past the technical reports rack. And on the technical reports rack was this paper by Larry on the Fisher information, which then was folded into and improved on by Andrew in the paper, as we heard from Oliver yesterday. And so we both think that how could that tech report have got there, because it was typically local things. And so we were thinking it was most likely me, but my memory is so hopeless that I wish I could claim credit, but we'll take it as plausible. And as Andrew said, so I must apologize for the typo at the bottom, but let's.
I think we're topically oriented, not chronologically oriented. So 2022,
yes.
2024.
It's the April part that I focused on. It was not. And so, as Andrew mentioned, in those days I was doing Poisson this, Poisson that, and so the late Brenda McGibbon and I were charmed by this circle of ideas, and we wrote a paper on a measure of information characterizing rare events convergence to Poisson. And then later on, very briefly, in this long work with David, we were in awe of the paper that Lucien and Pascal wrote with Andrew on model selection, and later the paper with Gilbert Leung on mixing least squares regressions. And then later on, Gaurav Mukherjee, who was here earlier, was my then student, and we worked together on Minimax prediction in sparse settings, and so we came to know about Feng and Andrew's work on Minimax prediction in the non-sparse case. So given Andrew's ongoing interest in central limit theorems and methods, I took the inspiration to speak about a tussle that we've been having lately with proving a central limit theorem for maximum likelihood. So this is a much more appropriate title for maximum likelihood estimation in generalized linear mixed models. And so I'll try to explain how it came to be that we were interested in this, because we were initially looking at some other class of estimators, and this was going to rely on maximum likelihood. And then it turned out that there was actually no proof for maximum likelihoods, no full proof for asymptotic normality of maximum likelihood in this setting. This turns out to be because of the latent variables causing likelihood integrals, that things get painful, as I'll say a little bit. And then I'll try to say how taking a complex variables approach seems to work quite nicely. I'll do this by talking about a toy example, generalized linear models without the mixed part, and then come briefly at the end back to mixed models. But basically, this is a very simple remark, this talk. And so I think there's considerable danger of embarrassment, either through error or through omission. So let's see if I survive. But I do want to say that this work is joint with an excellent student, Apratim Day at Stanford. So what is the setting? This one. So it's the very familiar and widely used setting of generalized linear mixed models. And so we have a large number of cases, or individuals, each of whom has a random effect associated with a collection of observations on that individual also assumed to be large. So this random effect is used to build in correlation among observations within cases. And then there may be covariates associated with each of the observations, and there will be parameters associated with these fixed effects. And so in the case that I'll talk about for focus, the chance of a response given the covariate and the random effect is say, a logistic function of the fixed effects and the random effect. And so the parameters of interest are the fixed effect parameter and the covariance of the random effects itself in a situation with many cases and many observations per case. And I'll come back to talk about the likelihood integrals issue. So let's, with apologies to those for whom this is all extremely familiar, a couple of slides to get used to it. So here's a simple data set from Matt Wand, or via Matt Wand, it's not his data. It's looking at this onycholysis medical condition, and there are two treatments, which I'll call red and blue. Individuals are the boxes, and so there's a series of observations around 10 to 15 over time on each individual, and then there's something like 300 individuals. And there'll be other covariates and the random effects and fixed effects of it.
Is one more severe and zero less?
That's right. Sorry, one is the more severe, but this is only orientation. I won't continue with the detail of the example. Okay, so in principle, one might want to think about maximum likelihood in this situation, and for each of the M cases, you have N observations, a conditional likelihood conditioned on the unobserved random effect, which you then need to integrate over. And so you get a collection of integrals, and if they're one-dimensional, you can be numerical about it without any real problem. But for example, in this widely used package, in dimension higher than one, the only numerical option is Laplace approximation, which actually turns out to be not so great in its inferential properties as when. Yeah.
So you could integrate that one using the samples.
When we looked, I guess this hadn't been. Maybe there were other things out there, but in terms of actual numerical performance. The way we got into this was that Matt Wand had adapted a variational method. The particular flavor was expectation propagation, which actually proceeds by a certain sequence of iterative KL projections to arrive at a particular instance of the evaluation of the likelihood. But that's for particular values, and then one has to numerically optimize. So this numerically works quite well. It's state of the art as of the paper. But the theoretical question was, is this asymptotically efficient? And the strategy for showing this, which is another talk, but let me just mention that the idea was to show that these EP estimates were sufficiently close to the maximum likelihood estimate that they simply inherited the efficiency of maximum likelihood. So all's well and good, except that trying to find an actual proof of maximum likelihood, well, important contributions in the literature, but not an actual full proof. So if you'll humor me to continue with this issue of proving the expected result, let me make some simplifications to focus on the issue. So let's first imagine that we just have a single covariate with a parameter beta, and then an intercept alpha, and a single random effect. And then the central limit theorem that one would expect has the limiting inverse Fisher information matrix there. Two things to comment before we go on. The rates are different for the parameters. For the slope parameter, there's a fast rate because there are m times n total observations that give information about a slope parameter. For the random effect, the sigma parameter, there's only m random effects that even if they were observed, you would only get a square root rate for them. Question? Oh. I'm sorry?
Yeah, so the EP of MME closeness, that's under, is there under what asymptotics?
Well, it's under M and N both large, and actually there is a relation between them, yes. In the example, the toenail example, M was 300 and N was 15. So its N is something like a power of M that's between 1 and 3 or something like that. So, yes, thanks. Coming back to so these are both M and N are large, and we would expect a root M rate for the variance component and also for the intercept, because you could think of that as a parameter of the random effect distribution, as the mean of the random effect distribution. So the same discussion applies. The second point is that this paper of Jimin Jiang and Matt Wand and Aishwarya Bhaskaran only recently gave a nice clean formula for the terms in the Fisher information.
Did they get those terms without even really knowing they had such a limit there?
Well, they say it is a standard result, but the point is that they calculate from the score functions using actually Tierney-Cascadane Laplace approximations. They compute the actual expressions for the Fisher information cleverly. But they take the ML result as given. So second simplification is to just focus on the fast beta parameter, assuming the intercept and variance are known, so that we just have this one-dimensional theorem for now. And so let's look at the log likelihood splits up into case likelihoods, where you have the n observations for each case collected up in the exponent here, and then integrated as we've been saying. And so it's sort of inevitable that you'll be using a Laplace approximation for the individual cases. And this is the usual form of the Laplace approximation, where, so R is this conditional log likelihood in the exponent, and it's maximized at a U star, and there's the curvature term and so forth. So that's the usual notation for that. Okay, so what could go wrong here? The way we teach maximum likelihood asymptotic normality is to take the log likelihood function and differentiate it to get the score function and expand it about the true value using, well, you can do a one-term expansion. The usual Cramer approach uses the two-term expansion. You rearrange to get the expression with the normalized score function at the true value in the numerator. That satisfies a central limit theorem. There's the observed Fisher information in the denominator at the true value. That's law of large numbers. And to quote from Ard's book, the only real challenge is to show that the third derivative is bounded in the classical Cramer approach. So Laplace approximations to try this. So let's look at this. So that the log likelihood is of a single case is, as we've said, we've got this factor of n multiplying the conditional log likelihood. So when you differentiate, you get the factor of n coming down and 3 terms involving the parameter of interest. So when you differentiate 2 more times to get the third derivative, you get 9 terms. But worse than that, this factor of n keeps growing on you, and you get something that's superficially of some high power when it should be order n. And so you have to have cancellations. And so in order to deal with the cancellations, you find yourself wanting to look at the higher order Laplace expansions, and moment cumulant relations. Things work, but you don't feel that this is really ideal. So with all of that, here comes the complex analysis tweak, which is to say, suppose that we can regard the log likelihood function as a function of a complex variable. For example, in some kind of a domain, an open connected set that contains the real axis, a strip for us will usually be fine. And suppose that you can establish that the average log likelihood converges for a suitable set of real values of the parameter. Then we can draw on these miracle results from very classical complex analysis to say that, oh, but now arbitrary order derivatives converge uniformly on compact sets in this neighborhood around the real line. And so we get this magical ability to take the second derivative at the nearby point that shows up in the simpler Taylor expansion and assert that that just does what we want it to do because of the uniform convergence and the strong consistency of the maximum likelihood estimate. Well, we're assuming that we have holomorphic functions, so differentiable function here on the real line that we can extend to be holomorphic, and then you get all the magic of infinite differentiability and so forth. But you cannot do this on the real line alone because you can't get uniform convergence of derivatives when you have only real analytic functions. So that's the reason for the complex analytic extension. I'm sorry?
You're not assuming real analyticity?
I'm not assuming, well, let's see.
You can extend it as real analytic.
So the examples that I will do will assume real analytic, and then we do the extension. But for example, you know, there is, you cannot characterize uniform convergence and compacts for derivatives using universal convergence. So that's the problem on the real line. So let's talk through this in a toy example where each step is very simple. That's taking a generalized linear model without a random effect, and we have IID pairs, but a single covariate. We have an exponential family, and then we can form the likelihood with a sufficient statistic in terms of these M observations and an average of the cumulant functions here. And so then the carrier drops out if we normalize by the likelihood at the true value. And then you have a simple expression for the average log likelihood, which certainly easily converges to a limit function for suitable values of beta. And we have convexity, so we have consistency of the maximum likelihood estimate. We take the two-term expansion in the simpler form. This has a simple central limit theorem, and we're left with this second derivative term to look at. So extending to the likelihood to a analytic function of a complex variable is straightforward in the exponential family situation because you look at the normalizing function of the exponential family, and as we teach in our courses, this is a holomorphic function for the real part in the interior of the natural parameter space. So long as this is not zero, you can take the complex logarithm and get a holomorphic function. So far, so good. And if we assume a bounded covariate, then a suitable strip around a real axis will give us this non-zero property for the logarithm. And so then we're in business because we can extend the individual likelihood terms to this domain, and we can define the log of the product to be the sum of the logs, which we couldn't in general assume, but because it's non-vanishing, we're actually okay. So this is a sort of a small point that one does have to be careful about. So let me state the convergence classics in more detail. So some definitions. This is holomorphic functions. Compact convergence is going to be just uniform convergence on compact subsets. A set of uniqueness is one on which, if the function vanishes on the set of uniqueness, then it vanishes on the whole containing domain. This could be as thin as a set of points with a point of accumulation, but typically an interval of real values will be enough for us. And so the Vitali-Porter theorem from 1903, 1904 says that if your sequence of functions are locally bounded on this domain, and you have pointwise convergence on a suitable subset of uniqueness, then you can conclude full compact convergence on the full domain uniformly on compact subsets. And then the Weierstrass theorem from even then a long time before says that if you have uniform convergence of holomorphic functions to a limit, then because you're dealing with holomorphic functions in the complex plane, you can carry that over to arbitrary derivatives. So you do need this epsilon of room around the real axis. That's the critical extra point. So to bring that back to our toy example, we have our average log likelihood compared to that at the true point. We do want to do this sample realization by sample realization, but on a set of probability 1 that's in the GLM case, it's easy to show that on compacts this is uniformly bounded because you just look at the properties of the cumulant function. And real convergence for a set of reals is just the law of large numbers that we talked about. And so now you just apply Vitali-Porter to go from the reals to this complex domain, and then get the derivatives, and then you use the strong consistency, and there you are. So that's the toy example. And I'm just going to say a little bit about the mixed model situation because there is a little bit of overhead in dealing with this case. So back to the mixed model setting. Now our case likelihoods are these integrals over the unobserved random effect. And the strategy, as we've been saying, is to make a holomorphic extension, checking that the extension does not vanish on a suitable domain, and then do the Laplace approximation, get the boundedness, and then conclude the limiting properties. The asymptotic normality in the numerator, I won't talk about. It takes a little bit of work, but it's simply triangular array, Lyapunov CLT, and it's actually not necessary to use Laplace approximations for the numerator. Okay, so the holomorphic extension for the case likelihood, the single case likelihood, involves this conditional log likelihood in the exponent, and that can be extended to be holomorphic in a strip like this, fairly plainly. But there is this factor of n, and this is now complex valued, and so now there's an imaginary part in this exponent. And so now there's an oscillatory aspect to this integral, and so you do have to worry about it potentially vanishing or not being bounded below and things like that. And so this little bit of overhead is the usual way to handle this sort of thing is to shift the contour from the real line to something that passes through a critical point, where the function in the exponent has a vanishing derivative. And fortunately, the contour can be taken parallel to the real line. So we shift the contour up there. And now we don't have to know too much about this critical point. It's enough for our purposes that it stays a bounded distance away from the unobserved random effect. The unobserved random effect is Gaussian, so it can be unbounded, but the critical point stays sort of suitably stuck close to this unobserved U, and we're staying within a suitable strip. And so we can get a uniform Laplace approximation, uniform in the complex parameter C, of the usual form, and that is enough to establish that with high probability this is non-vanishing, and so then you can extend that to the full likelihood with the product property and carry out the strategy as we did it in the simpler case. So let me wind up by making a small number of remarks about extending this to the initial case of interest. So we had variance parameters and an intercept parameter, and presumably one would want to have several covariates. And the Vitale-Porter-Weierstrass theorems work as well for several complex variables. This is part of what is called the elementary theory of several complex variables, and so nothing highfalutin is needed. And one does, of course, have to treat the fast variables separately from the slow variables. I've talked through mostly the logistic case. Everything seems fine for the usual families that are used for generalized linear mixed models. I've focused on the canonical link function. Certainly the probit link function should be addressable, but it does need to be thought about. And finally, having established some of these tools, one would naturally want to think about other situations with integration over latent variables. But let me pause and stop and say thank you for your attention, and thank Andrew for all his contributions and for this wonderful conference.
Thank you. Thank you. Time for questions or discussion?
Typically, here you assume latent distribution draw from Gaussian, right? You assume the
Yeah.
latent distribution
Yeah.
knows the distribution.
Yeah.
In Crumbs-Manning random effect models, the latent distribution, the U, we don't know which kind of distribution drawn from.
Right.
So that will end up with a semi-parametric likelihood. That model will become a semi-parametric likelihood, right? I wonder this.
So what's being used of the Gaussian random effect distribution is the properties of the rapid decay of the tails. Well, I mean, actually, I'm not.
You can think about using as a mixture of Gaussian to approximate true latent distribution.
Yeah, I'm actually not sure how strong, for this part, how strongly the Gaussian aspect is used, but it makes certain aspects very explicit. Thank you, Phil.
Yes, Mokshe.
Thanks for the beautiful talk. I was wondering, is it obvious that the set of real numbers on which you initially have convergence is a set of uniqueness so that you can apply the Vitale-Porter theorem?
Yeah, because you're doing things under the true value, and then you can basically show that the approximation is uniform over the appropriate set. And so I thought one was going to have to sort of use a countable set and throw away a countable number of null sets, but I don't think that's necessary, which is just as well, because in the several complex variables case, you need a set in the real hyperplane, an open set in the real hyperplane. So I think it's okay.
Okay, so you've shown a remarkable effectiveness of this combination of statistical and complex variable tools in identifying the asymptotic distributions, which is a central goal in large sample statistical theory. But we also resonate with the push from machine learning and information theory to have finite sample bounds. Is there any chance of a Bayesian type or other finite sample characterization of how close to normal you are?
I haven't thought about that because this is really a tool for this technical property of the denominator.
Yes.
And so the Bayesian stuff is, I think, largely going to come from the numerator.
Yes.
And so this is not really addressing that, I think.
Well, there certainly are efforts to give finite sample bounds for Laplace approximation, and maybe the log concavity of your integrand could help here. But this is delightful. I had not witnessed this power of complex variables in this setting.
The assembled multitude may have seen this somewhere. I'm just curious that with my terrible memory, I haven't seen it. But
yes. Great.
Question. So your domain now in a one-dimensional case, extending complex variables, your domain is an interval.
Yeah.
Okay. When you go to extend this to higher dimensions, if your domain are just regions, rectangular regions, I see no problem. But then when you get to connectivity, there is a problem, whether it's simply connected or not.
Yeah.
Yeah.
Yeah. So when I blithely talked about extensions to several, I was assuming products of intervals. Yeah. Because if you don't have connectivity, you can't get invariance of path in the line integrals.
Okay, thank you very much. Let's take Iain again.